In the last unit, we looked at the electromotive force induced in a loop of wire because of a changing flux in this magnetic field. And so we looked at how the flux changed through the loop of the wire in order to figure out the EMF, and then we can get the current. But we don't actually have to have a loop of wire to get an EMF. We can get it in a straight conductor moving through a magnetic field. And so we're going to start by investigating a loop and then change that to just the wire. So what I have here is this gray conductor is stationary, and across it is this other conductor that we're actually going to pull this direction. And it has a length L moving perpendicularly to this magnetic field. Now that's going to create a change in flux. And remember, EMF is equal to the change in magnetic flux divided by the change in time over which it occurs. But remember, magnetic flux is just the magnetic field times the area, and what we're doing is we're changing the area. We're not changing the field. So I'm going to say times the change in the area divided by time. Now let's think about this change in area. If this conductor moves from here to here, then it moved some distance delta x. And it did that in some time delta t, right? That's what we have down here. And so the area that it moved, the area that changed, is delta x times L for the length of that side. So this equals b times delta x L divided by t, or change in time. But if we look at that, that's just the equation for velocity. So I can replace that with b times L times v. And so I can simplify this whole thing to the equation: the electromotive force induced in this conductor due to its motion this direction is simply given by the magnitude of the magnetic field times the length of the wire times the velocity. And technically, it is the component of the velocity of the wire that is perpendicular to the field. So sometimes you'll see this written as sine theta. Okay? So the electromotive force induced in a wire moving through a magnetic field is given by that, and it's independent of this gray loop back here. That didn't really matter, that just got us set up for it. And so if we just actually take our conductor and move it through a magnetic field, a current will be induced in it. And so what we get is another way of looking at induced current. And what we can say is when a conductor cuts magnetic field lines, a current is induced. Now Lenz's law still applies to this situation, and if you think about this, Lenz's law says that the new current, the induced current, is going to create a magnetic field such that the new magnetic field opposes the change. So if we were moving this thing this direction, we were actually increasing the flux. There's more field in the loop, which means we're actually going to get a current this way through it. We're going to get a current down because that's going to create a magnetic field that goes in on this side, which tries to oppose the change, right? Since we were adding more field coming out, this new current is going to try to oppose that by putting a field in inside the loop. And so the current is going to be down. And so we actually get another right-hand rule that says for a conductor moving through a magnetic field, to figure out the direction of the current on the conductor, point your fingers in the direction of the motion, curl your fingers in the direction of the magnetic field, and then your thumb will point in the direction of the current. This sometimes is written another way, where you can say point your fingers in the direction of the magnetic field, point your thumb in the direction of the motion, and then the current is going to be in the direction of your palm. So on that one you would have to, it works out the same way, two right-hand rules to figure out the direction of the current through the wire. Okay. But this is just another equation for EMF, and I do like the idea sometimes of thinking about cutting magnetic field lines. So anytime a conductor cuts magnetic field lines, we get a current induced in that wire.